Okay, hello to everyone. I cut down the title a little bit just to make it more clear. So what I'm going to talk about is reliability of breeding values in selected populations. And before I start, I need to acknowledge my co-authors. That's John Hickey and Peter Baima. And this work actually started last year when Peter Baima had a presentation at the EAP meeting, and there were quite some heavy discussions about are his theoretical developments correct or not. And we were discussing this with Peter and Baima, and we decided to do a small simulation to test out his theoretical developments. So in our business, the reliabilities are important because they describe the potential change of estimated breeding values. So they tell us how the breeding values should be stable over time when we collect more information. But reliabilities or accuracies are also important in the breeding job because they tell us about how much response to selection are we able to achieve. And especially in recent times, we would compare different breeding programs regarding how much accurate, how much reliable breeding values are they giving us. And in the routine sense, we usually compute reliabilities from the prediction error variance, and as I will show, selection can reduce reliability quite drastically, and this is usually not taken into account. So just for example, I'm showing here a reliability of a parent average. So when we have no selection, we can work out the reliability, and this is the sum of reliabilities of parents multiplied by 1/4. But when we have selection in parents, for example, in this case, it's a truncation selection, the variance of breeding values in the parent population is reduced by a factor of 1 minus k, and this factor goes all the way up down to reliabilities. So in this case, the reliability of a parent average would be reduced by this factor. And for example, if we would have selection of parents, we would select 20% of parents, we can work out this k value from the intensity of selection and the truncation selection point, and this factor 1 minus k would be 0.22, which means that the reliability of the parent average would be reduced almost by 80%, which is a lot. So the aim of this work was to quantify the effect of selection on reliabilities computed either through prediction error variance from the routine genetic evaluations or via squared empirical correlation between the estimated and true breeding value. And we wanted to compare those figures with those what we would get from the theoretical developments by Peter. So just to show you what Peter derived is a set of equations for so-called empirical reliabilities. So if we would have selection in a population over time, a Bullmer equilibrium would be achieved, and if the reliability of breeding values at the time we would select parents is 0.8 and it would be equal between both parents, so we would have no difference between parents, and we will also select the same proportion of parents. You can see that in above line, the reliability in such a population would not be decreased a lot if we would increase the selection intensity, but the reliability of a parent average is quite severely reduced. And so we did a simulation. We simulated something like a genomic setting. We did it in 2 steps. First, we ran a coalescence simulator to obtain haplotypes nicely structured with a proper LD structure. We had 4,000 of these haplotypes for 30 chromosomes. In this step, the coalescence simulation included mutation and recombination, as well as the drop in effective population size, as we would see, for example, in the Holstein cattle. And the next step, we would took those haplotypes and we would randomly assign them to founders of the population. And these founders were then the haplotypes of these founders were then dropped down through the pedigree. We had several generations in our pedigree, and in each generation, we would have 50 sires, 10 dams, 50 sires mated, each of them by 10 dams, and they would jointly have 4 progeny, altogether 2,000 animals per generation. We were also allowing for recombination in the dropping phase, The QTL effects were sampled from a Gaussian distribution. In order to make the simulation a little bit easier and in order to mimic a little bit the progeny testing, we assigned the phenotypes only to males, but we pushed up the heritability quite strongly. So the phenotypes were only on males, but highly heritable. And we were either doing random selection of sires and dams, so no selection, or we would obtain blob values for all the animals in generation, and we would select the best 50 for sires and the best 500 for dams. And all this is implemented in the AlphaDrop software, so if anyone wants to repeat a similar exercise, you can email John and he'll provide you with the software. So in essence, what we have is the above table shows you the layout of our generations, our simulations. So we had 25 generations in our pedigree that were divided in few chunks. So the first 10 generations, we just wanted to obtain enough pedigree information, and in those first 10 generations, we didn't do any selection. But then we had two scenarios from generation 11 forward. We either had selection or no selection. That's on the blob EBVs. And of course, for the old time, we had pedigree information as well as the true breeding value information. And for our analysis, we assumed that the phenotypes are available only for animals in generation 16 to 20. These are only males. And since half of them are males, we would have 5,000 phenotypes. And we also assume that the genotypes are available for those 5,000 phenotype males, but also for each 500 animals in the next generation from 21 to 25, which were the validation generations. We ran the analysis with a pedigree and genome-based animal model. We estimate the variance components with REML, and conditional that we computed the blobs. Everything was done in AS-REML. And since we did it in a sequential steps, we had the information, the estimated breeding value as a parent average, then after so-called progeny test, this would be EBVA, and of course with the genome information, this would be EBVG, and we computed the reliabilities either through prediction error variance or from the empirical reliability. So as a result, I'm going to show you the same table twice, without selection and with selection. What you can see in this table, it's a lot of numbers. I don't know, does this work? Yeah, it does. So we have prediction error variance based values and the empirical correlation. So we have generation 20 divided into all animals, males and females. The parent average reliability is about 24, and you see that more or less we get a match with the empirical reliabilities, and the same one for the progeny tested one, and the genomic one fits quite nicely. And then in the validation generation, when we don't have phenotypes, we can also, with the pedigree models, we can also get the parent average, and of course this prediction, the reliability of this prediction goes down with time. The genomics does work better, but we also see decrease due to recombination between the QTL effects and the SNP markers. And again, we see quite nice match between what we assume from the mixed model equations and what we see with the empirical correlation. Now, if we have selection in our population, just briefly to see if you take a look at those, if you take a look at this block of numbers, you would see that when we have selection, the mixed model does account a little bit for the selection effect. But if we check what's the true reliability, what's the correlation between the EBV, between what we estimate and what's the real situation, you can actually see that there is a huge difference, and that's especially for the parent average. So the parent average in the selected population has really, really low accuracy. Of course, the phenotype-based breeding value has quite good reliability, and the genomic one works more or less as we would expect. And we compared what I'm showing in this slide is a 3D plot as a contour, and the contours are based on the equations that Peter Beimer derived. And in the previous slide, you saw that that the empirical reliability that should be squared is 3%, and we see that with the proportion of selected sires we had and dams, you see that more or less with our simulation we are confirming what Peter did from the theoretical side. So why bother? I've heard quite a lot of times that people are complaining or reporting that the reliabilities of parent averages are a bit weird because we usually don't see the realization of those reliabilities is much lower, and people are attributing that to preferential treatment of bull dams or perhaps some non-additive genetic effects in the bull dams. But as you can see, selection can also be an additional reason for that. And results I have shown are also important for the genomic setting. Why? Because when we are comparing breeding schemes based on reliability of parent average from the mixed model and the reliability of genomics based on the cross-validation, we usually underestimate the value of genomics. So the genomics is much more useful than we are actually reporting. And of course, another issue which implies from our work is that when we blend the parent average with the genomic-based breeding value, we use the accuracy for the parent average, which seems to be too high. So my question is, should we actually do this or not? And I wonder if the single step is actually basically doing the same stuff. So the single step approach would also have the same issue. With that, I would like to thank you.